think we want to go on and hear the other side of the story of how you can develop potential drops along the field lines. Dr. Lars Block will talk on electrostatic double layers.
The reason why I believe in double layers is that they are so easily produced in the laboratory, and I'm going to show at first some evidence from laboratory experiments. The first slide, please. This is a picture of a double layer in a gaseous discharge tube here. Sorry?
It's upside down.
It's upside down, yes. There is an arrow here, and that shows the position of the double layer. I don't know if you can see it, but it is a darker region just here.
It can see.
And it can be seen with the bare eye. It's not a short time experiment. This is a DC experiment. It can go on for hours. Now, some people say that these double layers are an effect of the walls, but this is not true, because you can produce double layers even in a discharge which is detached from the walls through, for example, a longitudinal magnetic field. In fact, they are even more easily produced in such a case. Oh, they all seem to be upside down. Well, it doesn't matter here. This anyhow shows how, with a simple theory of a stationary double layer, how the potential down here varies through the double layer, and the electric field and the space charges. It's called a double layer because there are space charges of opposite signs at each end of the double layer. The thickness, typical thickness of a double layer is of the order of 100 debye lengths. And the typical potential across a stationary double layer is of the order of maybe 5 or 10 kT over E. But in some double layers of short duration, it can be much higher. And I will show evidence of that in the next few slides. Actually, this is an idealized calculation of a stationary double layer, but most double layers are fluctuating. Well, this is shows some fluctuations that are occurring in a discharge tube shown here. And you see 3 different positions here where measurements have been made with probes in the discharge, showing fluctuations of the potential at these 3 different positions. Positions 2 and 3 here are very close together and are on opposite sides of the double layer itself. And we see here from position 1, which is on the cathode side of the double layer, the probes are the probe voltage is with respect to the cathode in all cases here. And here are shown fluctuations of the potential at this position, which are of the order of, the scale here is 1 volt per division here. Then in position 3, on this side, on the anode side of the double layer, you see these fluctuations here, and there the scale is 100 volts per division. So the interpretation of this is that the double layers are formed and disappear. They are not quite stable and then they appear again, and they repeatedly appear at the same position. Now these other curves show about the same thing. I haven't time to explain them in detail. This shows how the characteristic potential against current for the discharge itself. If you have a low current, you go along this characteristic. It's a discharge, an arc discharge, so the currents are of the order of amperes. You have a linear scale here with 10 amperes here. And the cross-section of the discharge is a few square centimeters. But then one can see that during these, if you have these low currents, then you have fluctuations at various positions in the discharge, and there is no double layer. These fluctuations are of the order of a volt approximately, the amplitude of these fluctuations. But once you get to this position of the order of 10 amperes here, the fluctuations increase quite a bit. It's shown here in these fluctuations are shown here with different scales: 1 volt per division, 5 volts, 10 volts, 20, 100 volts per division, corresponding to these various points on the characteristic here. And then suddenly the potential across the discharge jumps up from about 70 to 100 volts here, indicating that the average DC component of the potential across the discharge is of the order of 30 volts. This shows probe measurements of the electron density and electron temperature in the discharge at various currents, and the temperatures are of the order of 30,000 degrees, the electron temperature, and what is important here is the lower row of figures here, which are of the order of 0.2, 0.3, 0.39, 0.33, 0.32, 0.26, and so on. And that gives the ratio of the average drift velocity of the electrons over the electron thermal velocity, showing that even if you have a very weak current, this is 0.1 ampere and here is 10 amperes, even if you have a very weak current, the drift velocity is quite high, much higher than the ion sound velocity, for example. But still, the conductivity is determined by the ordinary collision theory, showing that the two-stream instability, which should develop at much lower velocities, does not affect the conductivity really. And I think that is due to the fact that the distribution is not Maxwellian. Then after the current has been increased sufficiently much, then the double layers appear when the drift velocity approaches the electron thermal velocity. Measurements of the total density, total gas pressure, that is the ion pressure plus the neutral gas pressure in the discharge, show that there is a pressure minimum between the cathode and the anode, and that the double layer occurs at this pressure minimum. This shows some topside sounder experiments by Hertzberg and Nelms, the Alouette data, and these show some similar depressions of the density at about 200 kilometers altitude here, and I suspect strongly that this could be a region where double layers would form. I have asked Louis Hertzberg about the reality of this, and she thought that this was a real effect that they saw. And they saw these several times in regions where the electron density was much lower in the topside and F region than normally. And I suspect that these occur where field-aligned currents are flowing. These are measurements at the Indian 5 satellite of inverted V events. Lou Frank has produced this slide for me, and I show this also with permission of Rita Sagalin, who measured the electron density on the same satellite. And it was found in this region we have inverted V events, and in this region also the electron density was decreased by more than an order of magnitude. Because of this pumping effect of the field-aligned currents that I have also given theoretical evidence for in some papers in Cosmic Electrodynamics a year ago, one should expect that the double layers occur in this low-density region, but once these double layers occur, that corresponds to a higher resistivity of the circuit, and therefore the currents would avoid this region and move sideways. These are calculations by Lennartsson, where he has assumed at 1200 kilometers an electric field reversal of this kind, and at the same time he has an enhanced he has here an enhanced resistivity in this region, and then he solves the equations and finds that the maximum field-aligned current is outside the region of the enhanced resistivity, which what I mean with this is that you would not necessarily expect that double layers would occur where the field-aligned current is maximum. Well, I had some comments on how to discover double layers too. This is the last slide. If you make double probe measurements of electric fields in the ionosphere, you should look for spikes, because when the rocket goes through a double layer, which is very thin, you only see the strong electric field for a short time, and you should not discard these spikes. Also, one should look at pitch angle distributions of particles near 90-degree pitch angles. This has been done by Albert and Lindström, who has published a paper in 1970 on that, and I think I would recommend rocket experimenters to study that paper and repeat that experiment. And one can also look at topside sounders, as according to the data that I showed in the previous slide by Hertzberg and Nelms. And one should measure electron densities by Langmuir probes or ion traps or any other such devices. And also one could shoot an electron beam from a rocket or for example from the shuttle when this is in operation, and see how they are reflected by the double layers and look for the return fluxes. This has been proposed by Gustafsson in Kiruna. I don't believe that barium clouds would be good because they would probably destroy the double layers. Well, in general, I would recommend coordinated measurements with magnetometers and electric field measurements on the same rocket to see if the parallel electric fields are located where the field-aligned currents flow. Thank you.
Yeah. I got the microphone, I guess. This question is directed to both of you anyhow. Since both the double layers and the anomalous resistivity seem to involve currents and fluctuations, is it possible that you're both just using different names for the same type of phenomena with perhaps the, I mean, am I just ignorant, or with the scale length here just being shorter?
I think that is possible. I think perhaps that the what people call the anomalous resistivity actually develops into double layers, which are not, as you have seen here, always stable, but they occur and they disappear and occur intermittently.
Well, distinguish between the two, apart from the absence of.
Well, I think they are actually. I think they are actually the same thing, and
Well,
you need not distinguish between the same thing.
you don't require any wave turbulence associated with the with the double layer, whereas.
Well, it depends on what you mean by turbulence. This is a one-dimensional turbulence. Then, if you could talk about one-dimensional turbulence, that's possible. I don't know.
Well, I had a question and also an answer to his, I guess. My question was, do you have any experimental evidence that double layers don't form except near walls?
Yes, oh yes. We have had experiments with magnetic fields which have confined the plasma so that it's far detached from the walls. It's not at all in contact with the walls. And the double layers appear even more easily then.
And the other thing is that don't you, when you talk about turbulence, you essentially you're depending on drift velocities greater than the thermal velocity, is that correct?
They are far greater than the thermal velocity of the ions. And according to the two-stream instability, this should develop, the theory of the two-stream instability, it should develop if electron temperature is much higher than the ion temperature, the two-stream instability should occur for drift velocities of the order of the ion sound velocity. But they don't occur in these experiments, presumably because the distribution is not Maxwellian.
What was your ion plasma temperature in the experiments? Did you measure it?
Yes, the ion plasma temperature is of the order of 1,000 degrees or so. I cannot give any exact figure of that.
Can I answer his question, which was the mechanism that I gave in the second part of the paper did not depend on current-driven instabilities, and all it depended on was enhanced fluctuation levels as another method of getting anomalous resistivity.
In general, the velocity distribution is not Maxwellian in gaseous discharge. Whenever you have a current, it's not Maxwellian. It's not just a drifting Maxwellian distribution. So calculations based on Maxwellian distributions are not applicable here.
Well, then how can you claim that it is beyond the current-driven instability, since the current-driven instability is based on Maxwellian distributions?
No, but
the phenomenon of the ion acoustic velocity comes in is based on essentially Maxwellian type distributions. And
yes.
It seems to me that you have to calculate what the threshold is for your current-driven instability based on the distributions that you say you have.
Yes, I mean that the drift velocity is far higher than the average random velocity of the particles. But this is not a Maxwellian distribution. I mean, you can you have a certain spread of the velocities, of course. You don't have a monoenergetic distribution, but you have a spread of the velocities. But this is not of a Maxwellian type.
I think we should go on to another question.
I just have one question. It strikes me that there's considerable J.E joule heating across the double layer, and I'm wondering how this energy is dissipated in the magnetospheric case or the ionospheric case.
Oh, in the magnetospheric case, it is dissipated through acceleration of the particles that go through the double layer. These particles get high energy, and then when these particles are interacting with the plasma or the neutral gas further down, then of course their energy is dissipated. In the experiment, it is dissipated when the particles hit the walls further away, a little bit away from the double layer, and this dissipation is so strong that it can melt the walls. If you're not careful and switch off the current in time, you will melt the wall.
So the only current flowing across the double layer is the energetic particle current?
Yes, they come into the double layer with approximately thermal velocity, and then they are accelerated to higher velocities, corresponding to the potential drop across the double layer.
I see.
One last question.
I wanted to comment that James at CRC is using some of the ISIS data, ISIS 1 and ISIS 2, and he's been studying VLF-Vs. And what he's been doing is ray tracing back to the field line of the center of these Vs, assuming these are Whistler mode waves in the electrostatic Whistler mode wave. And in ray tracing back all these various frequencies, he has arrived in some cases that the source is concentrated in a region less than 10 kilometers long along a field line. So there's a couple of questions. Is one, do you expect any VLF emissions in these regions? By the way, the field lines from which these emanate are not in regions of particle precipitation, but in fact in between these regions, so it's probably field-aligned currents. So one, do you expect any VLF emissions in this process? And two, wouldn't just about any instability tend to concentrate itself into short lengths, simply because as the resistance goes up, the potential across this small length of the electric field goes up, and therefore the resistance goes up, and therefore the thing gets shorter again, and wouldn't you expect just about any instability to go to very short distances?
I don't understand your last argument. I would expect VLF emissions from these because of their fluctuations. But this, I have no quantitative estimate of that. But I don't see why it would concentrate. In fact, it is true that it does concentrate into thin regions, but...
Would practically all other instabilities do the same thing, though? Simply because the electric fields become stronger, and therefore the instability grows. Therefore, the electric fields become stronger.
That may be right. I don't know.
I think we want to go on to the last talk.